Hi, I'm Dr. Christopher Sutton. Welcome to my introduction to GIS video series. In this video, we will discuss the classification of map projections based on what is called the developable surface. Developable surfaces provide the foundation for many map projections. When we use a developable surface, features of Earth are projected onto the surface, which is then flattened. In GIS software, the transformation of locations on the globe to a flat map is done automatically. While we rarely use physical media for developable surfaces, examining the projection process in the context of various surfaces helps us understand what happens during the projection process. There are three primary developable surfaces used in the map projection process, and you often see the surface type included in the name of the projection. The developable surface types are a plane, a cylinder, and a cone. Creating map projections using developable surfaces is a multi-step process. The first step is to position the surface over a representation of Earth known as a reference globe. Once Earth's features are projected onto the surface, the cylinder and cone are unrolled to a flat map. A plane is a flat surface by default. When placing a cylinder, cone, or plane, we typically consider the surface's contact method and orientation relative to the reference globe. The contact method for a developable surface is its case, and the orientation is its aspect. There are two types of projection case: tangent and secant. In the tangent case, the developable surface is placed so it contacts the surface of the reference globe. In the tangent case, cylinders and cones touch the reference globe along a line, and a plane touches the reference globe at a single point. In the secant case, the developable surface intersects the reference globe, passing through it. In the secant case, cylinders and cones intersect the reference globe along two lines, and a plane intersects the reference globe along a single line. What is the importance of understanding projection case? One of the most important things to be aware of is that there is zero distortion in the map where the developable surface touches the reference globe. If the contact is along a line, that line is called a standard line. If the contact is at a point, that point is called a standard point. If the map you are making covers a large area, secant case projections tend to have less overall distortion than tangent case projections. Let's examine the distortion of these three surfaces with the tangent case and then the secant case. In this cylindrical projection, the developable surface is wrapped around the reference globe and is tangent at the equator. The equator is the projection's standard line. Thus, distortion is zero along the equator, and it increases with distance from the line of contact. In this tangent conic projection, the standard line is in the mid-latitudes. Like with the cylindrical projection, distortion increases with distance from the standard line. In this planar projection, the developable surface is tangent at a single point. There is no distortion at the point of contact, and distortion increases with distance from that point. Like in tangent projections, in secant projections, distortion is minimized along standard lines and increases with distance from those lines. As noted previously, secant projections have less overall distortion than tangent projections when mapping large areas of the planet. The aspect of a projection refers to the orientation of the developable surface relative to Earth's rotational axis. By changing the orientation of the developable surface, you can achieve different results. There are three aspects. The first is the normal aspect. With normal aspect, the developable surface is oriented so its axis aligns with Earth's rotational axis. For planes, cylinders, and cones, a normal aspect produces the simplest geometry in the depiction of latitude and longitude lines. For cylindrical projections, the cylinder is wrapped around the globe tangent along the equator. For conic projections, the apex of the cone is placed above one of the poles, and the developable surface contacts the reference globe in the mid-latitudes. For planar projections, the plane touches the globe at a pole. The second aspect is transverse aspect. In this orientation, the developable surface is rotated 90 degrees from the normal position, so its axis is perpendicular to the rotational axis. In cylindrical projections, this means that the developable surface makes contact with the reference globe along a longitude line instead of the equator. A conic projection is oriented so the apex of the cone is above the equator, and a planar projection will touch the reference globe at the equator. The final aspect is the oblique aspect. In this aspect, the developable surface is oriented at an angle that is neither parallel nor perpendicular to the rotational axis. How do we see these projection aspects used in mapping? Cylindrical projections using a normal aspect are used for world maps and mapping the low latitudes. Conic projections using a normal aspect are used when mapping the mid-latitudes. Planar projections using a normal aspect are used for mapping the polar regions. Transverse projections are commonly used in large-scale mapping of areas with predominant north-south extent. The transverse Mercator projection is a widely used example. Oblique aspects are typically used for mapping areas that are best represented when the central line of projection is diagonal, such as island chains or features with a northwest to southeast orientation. A later video will expand on choosing an appropriate projection for your mapping purposes. In the next video, we will discuss a final way to categorize map projections, as there are projections that do not attempt to minimize a single distortion property, nor are they created using a developable surface. I'll see you in that video.